Have you ever been on a bike riding down a hill and found yourself going pretty fast? And did you notice that as your bike moved faster, it felt as if your body was being pulled back, as if something was dragging you? What is this force? Well, it actually has a name. It is, you guessed it, drag. For professional bikers, this force becomes very important as they are battling for split-second advantage. As shown in this Ansys computer simulation of a cyclist in motion, we find that as you lean forward or crouch down in your seat, the drag force becomes smaller. We also discover that as the bike picks up speed, the drag force gets larger. Why is that? Well, in this video, we're going to explore the drag force and examine how it works. We will also show how Ansys simulation technology around the world is used to understand the drag force. From bike designers exploring funny-looking helmets, to NASA scientists safely landing space shuttles, and even F1 car designers creating the fastest cars on the race circuit. Are you interested? Well, let's go. When objects move through fluids like air or water, they experience a force that tries to stop it from moving forward. This is called the drag force or fluid resistance. Simply put, drag slows you down. We found this out when we were riding our bike. You have to put some effort into pedaling the bike just to keep yourself moving forward. But did you know that the drag force from a moving fluid can also push on things at rest and make them move? If you put a large board over your head with the flat side facing the wind, you'll really feel it pushing on you and probably have a hard time keeping the board over your head, especially if the wind is strong. Wow! For vehicles like cars, trains, and airplanes, which move at fast speeds, it turns out that drag is very important. Let's talk about airplanes for a moment. There are four main forces which affect how an airplane flies through the atmosphere. And these forces are lift, thrust, weight, and drag. Lift keeps the plane in the air, opposing the plane's weight, while the thrust moves the plane forward. The drag force acting on the plane opposes the thrust force. Because of its size and speed, the drag force is actually quite big. I mean, really big. How big? Let's just say it's like a herd of 25 elephants pulling you back. That's crazy. To overcome this drag and move forward, you need more thrust, which means you need a bigger engine, and then you need a bigger airplane to hold the engine, which means a bigger wing, because now you have more weight, and yikes, this is getting out of hand. Let's take a closer look at what drag really is. When fluid flows over an object, the object experiences two forces, a friction force and a pressure force. Let's go to my lab and find out more about them. Here's my lab. No. My laboratory. Let's first talk about the friction force. Fluids, which include both gases and liquids, are generally sticky substances. That is, they want to stick to the objects that they flow over. The amount of stickiness a fluid has is called the viscosity. If the object is a bike, or an airplane, or any other moving body, the viscosity of the fluid will want to oppose the direction of travel, and therefore slow the object down. This is the friction force. Let's take a closer look at this with an experiment. I have 4 tall glasses filled with different liquids: water, corn oil, glycerin, and honey. These liquids have different viscosities from low, the water, to high, the honey over here. I have 4 marbles with the same size and weight, and I'm going to drop these marbles into each fluid. Watch what happens. Notice that the marble reaches the bottom quickest in water and slowest in honey. This is because for higher viscosity liquids, the friction force is greater and slows down the marble more. The main thing to remember is the higher the viscosity, the larger the friction force. But what about gases like air? They have viscosity too, but it's much, much smaller than liquids, especially something as sticky as glycerin or honey. So fluid friction by viscosity causes a drag force, and this force depends on the surface area of an object. The larger the surface area, the higher the friction force. But that's not the whole story. It turns out that if the pressure of the fluid flowing around our object changes a lot, that can cause a drag, which we call pressure drag. Do you remember what pressure is? Pressure is the force exerted by a fluid pressing on an object. If you pump air into a balloon, a soccer ball, or a bike tire, you know that the air inside has a higher pressure than the outside air. The pressure of the inside air exerts a force that pushes on the walls of its container that you can feel. For example, the surface of this balloon. It's like the air inside is wanting to get out. What if I let some air out?
Look! The force is less and I can easily press the side of the balloon with my finger, so higher pressure equals a larger force.
Now let's look at the pressure as the air flows around an object. This flowing air has energy due to its motion. But what happens when suddenly the air hits a surface? Wham! The air has to stop, which causes the pressure in front of the object to go up. Higher pressure means a higher pressure force. This force will act on the front of the object and will try to push it back. If you've ever used a hairdryer like this one, you've probably felt this pressure force if you pointed the dryer directly at your hair. Whoa! I can feel that! This same effect happens with vehicles in motion like bikes, cars, and aircraft. Using computer models called simulations, you can visualize the airflow around these vehicles. You can build and analyze these models, such as a full-size airplane shown here, right now directly on your computer using Ansys simulation technology. Here are the results of our simulation. The red region means high pressure. We can see that high pressures show up in the parts of the plane facing the airflow. Makes sense, right? Now let's zoom into a section of the wing, which by the way is called an airfoil. Because of the shape of the airfoil, the air moves faster along the top compared to the bottom side. This creates a pressure difference that results in two types of forces: a lift force, which keeps the aircraft in the air, and the pressure drag force, which pulls it backward. Remember, the friction drag is always acting on the airfoil, and the total drag is the sum of the pressure and the friction drags. If we now start rotating the airfoil, the pressure difference keeps increasing, and so the pressure drag also increases. As we keep increasing the rotation angle, the airflow can no longer follow the shape and completely leaves the surface of the airfoil. This phenomenon is called separation. It's kind of like what happens to a car when it tries to make a sharp turn too quickly and skids out of control. Ouch! When separation happens, the flow breaks up into a swirling, churning river of fluid, and the pressure of the fluid drops in the area where separation occurs. Due to this, there is a huge increase in the pressure drag. Fun fact, the pressure drag will be much, much bigger than the friction drag after separation. We now know that drag comes from fluid friction and pressure differences, and that separation can have a big impact on drag. What else can we discover about drag? Let's go back to the lab. Here we have two toy cars. One small and the other large. both having the same weight. Notice that we've added 2 coins to the smaller car to make its weight equal to the larger one. Now let's blow air onto the cars, one at a time, and measure how far the cars get pushed back. Here are the results of this experiment. We see that the larger toy car gets pushed back more. Any guesses why? This is because the amount of drag depends on how big of an area the object has when it's facing the flow. The bigger the object, the bigger this area is and the larger the force is. Now let's do another experiment. Take one of the cars and see what happens when we reduce the flow speed. The car is not pushed back as far as before. This is because the drag force on the car is smaller. The lower the flow speed, the lower the drag force will be. We've seen how fluid drag can be a real drag and slow you down. But we don't want to go slow, do we? So how do we reduce drag? Well, we can make our airplane really small, which would reduce the area of the airplane facing the flow. But hey, we want to be able to carry people and not mice in our airplanes. Or we could also slow our airplane down. But then we would not be able to leave the ground. Bummer! So what can we really do? A more practical way to reduce drag is to make the shape of our object sleeker. This reshaping is called streamlining. Aircraft designers figured out that if you wanted to fly faster, you needed a smooth shape. Even the automobile and train designers got into the streamlining business. After all, lower drag means less power consumption and higher efficiency. Let's learn more about streamlining. I'm back in the lab where I've set up an experiment which will help us observe the drag forces produced by different shapes. The setup can be built from common materials you can get at any hardware or home supply store. The 3 foam models are a rectangular shape, a half circular shape, and an oval shape. Each is 28 centimeters long and 7.8 centimeters high, which gives them the same frontal area with respect to the airflow. The models are mounted on 2 vertical poles attached to a sliding wooden platform. Air from our blower is directed over the foam models, producing a horizontal drag force. This drag force is resisted by a spring which permits the platform to deflect by an amount proportional to the force. The greater the drag force, the greater the deflection. The amount of deflection is indicated by a simple scale on the side of the test setup. A needle is attached to the pole so you can easily read the deflection. Okay, let's start blowing air over these shapes and record the deflections for each one. First, we'll look at the rectangular block shape. Notice the deflection indicated by the needle. Next, let's look at a half circle shape. Wow! The deflection is dropped quite a bit simply by having a rounded front shape. Now let's test this streamlined oval shape. Notice how the shape is smooth and rounded at both the front and the rear. Hey, the deflection is even smaller still. Here's a plot of our results. We repeated the test 5 times for each shape and averaged the measurements. We can clearly see that by simply providing smooth surface shapes at both the front and rear of an object, we can significantly reduce the drag force. This, in a nutshell, is what streamlining is all about. As you will see later in our simulations of these shapes, This effect is mainly because of a reduction in the pressure drag due to separation. Fun fact, you may have noticed that the streamlined oval has a higher surface area, so the friction drag actually increases. However, the reduction in the pressure drag is much higher, so the total drag force will still be smaller. For those of us who don't want to build an experimental setup like this, we can use computer simulations. Scientists and engineers around the world rely on Ansys simulation technology to accurately predict drag and improve designs. Let's look at the streamlined oval shape. Here you can see the air pressure on the surface of the oval. The red color means high pressure, and the blue means low. As we discussed earlier, a high pressure means a higher pressure force. This means the force on the front side of the oval is larger than its back. Because of this, the oval experiences a net push in the flow direction, and this is what we call the pressure drag. Also recall that air has viscosity, and the oval feels a friction force which also pulls it in the direction of the flow. This is the friction drag. The overall drag force, therefore, is in this direction. Here are the simulations of the foam shapes. You can see the pressures in the fluid. The greater the pressure differences over the body in the flow direction, the greater the drag force. You can also look at the velocity and see the amount of separation. In fact, we can directly calculate the drag force on each shape. Here are the predicted values of drag force for our shapes. Notice that the friction drag goes up for the streamlined shapes because of the increase in surface area exposed to the moving fluid. However, the pressure drag decreases because of reduced separation. Recall that we said that the total drag is the sum of both the friction drag and the pressure drag. So as the shape becomes more streamlined, the total drag goes down. Let's now use this Ansys simulation technology to see how engineers design cool streamlined applications. Here we have two trucks. Can you spot the differences? The one on the top is an older traditional design, and the one on the bottom is a modern and aerodynamic design. If we look at the pressure distribution at the front of the two trucks, we notice that there's a large high pressure zone in the front of the trailer on the older design. The modern design smooths the airflow over the top of the cabin thanks to a deflector reducing the drag significantly. If we now look at the velocity distribution around the trailers, we see that the blue-colored region behind the modern truck is smaller compared to the older truck, indicating less separation. This is because of the attachments on the modern truck, which help reduce the pressure drag by reducing separation. And due to reduced drag, we get better fuel economy, which is good for the environment. And your wallet. Formula One cars use this really cool technology called the drag reduction system, or DRS. In the straight sections of the racetrack, with just a push of a button, you can change the orientation of the wing to reduce the area facing the airflow. This reduces drag and allows the car to go faster by about 15 kilometers per hour. Zoom! You may have seen these weird-shaped helmets used by professional bikers. The streamlined shape reduces drag compared to a regular helmet. For professional bike racers, this could be the difference between winning a race and coming in second or third. Finally, I should mention that drag is not always a drag. There are lots of situations where we want to slow down. For example, a parachute is designed to provide enough of a drag force to slow down a skydiver so that they can land safely. The inside of the parachute experiences a higher pressure, which is indicated in red, compared to the outside. This pressure difference between the inside and outside is responsible for creating a drag force, which allows the skydiver to dramatically slow down before landing. The pressure drag can be visualized by the massive flow separation behind the parachute. You may have seen parachutes deployed behind a dragster or even space shuttles. Again, the idea is to slow down the vehicle so that it can safely come to a stop. Thanks for joining me today, and I hope you enjoyed this video. Be sure to hit the like button below and subscribe to our channel. Also, check out the other videos in this series.